AI seems like a buzzword that's just as vague as it is popular. And if we're honest with ourselves, the concept of quantum computing might feel just as mysterious or even ominous. In a prior podcast, we took a crash course in explaining the basic nuts and bolts, or should I say, ones and zeros of AI. For those that missed it, the link is in the description. In this episode of the HMNS Beyond the Bones podcast, we'll attempt the same in creating a basic understanding of quantum computing. So, hold on to your qubits, and let's try to make sense of quantum computing with our layman 386 brain. That was a computer joke for any of you just as geeky as I am. Anyway, I'm your mental curator, Johnny Hemberger. And honestly, sometimes I can't sleep at night if I catch myself dwelling on the Pandora's box that might be the marriage of AI with quantum computing. In my opinion, it will make the crossroads of humanity at the birth of the nuclear age look like a split in the path on a beginner hiking trail compared to a Houston freeway interchange at 5:30 p.m. on a Monday. It could be a point of no return. More succinctly, again in my opinion, it could be humanity's event horizon, period. We are Eve pacing nervously while we can't take our eyes off the apple. Truly, I tell you, this is how important AI and quantum computing could be to humanity. However, I don't mean to scare you. Yes, we invented the atomic bomb, but the understanding of nuclear energy has also saved countless lives when applied to the field of medicine. Similarly, while yes, AI and quantum computing can be wielded negatively, it can also improve our lives beyond our wildest comprehension. For just one example, not only could it potentially be used to treat and eradicate cancer with cellular atomic precision per individual with virtually zero side effects, but it could also theoretically be used to poison people with certain DNA markers if it fell into the wrong hands. As with any breakthrough, it entirely depends on how it is used. The ethics of it all is truly mind-boggling. I asked our very own illustrious director of IT, John Schockel, for his take on quantum computing.
Successful quantum computing will result in modeling and simulation of humanity's most difficult problems at speeds many orders of magnitude faster than current technology. This computational power will lead to rapid advances in nearly every field, including pharmaceuticals, healthcare, material science, logistics, and transportation. Similar to how the industrial age and the digital age resulted in rapid technological and economic advances for humanity, the quantum computing age will thrust humanity ahead at an even faster pace. That being said, successful quantum computing is not guaranteed. There are physical problems such as inherent quantum instability, and there are engineering problems such as a high cost, difficult scaling, and the lack of algorithms for quantum computing architecture. And then there are societal problems, such as the resulting vulnerability of all current security protocols, which are used for privacy protection, banking, national security, and many other things. Although the solutions to these problems seem within humanity's grasp, they remain out of reach.
Perhaps with all that being said, that's why we are understandably apprehensive about looking behind the curtain. But in my opinion, again, it is precisely the pursuit of understanding that reduces fear. As anyone who has seen Star Wars will tell you, it is fear that breeds hatred. Can I riff for a moment? Anger and fear are like a safety blanket. That's the entire playbook of social media, talk radio, and the 24/7 cable news channels. By the way, you're not getting the quote-unquote news. You're getting commentary disguised as news. All designed to keep you engaged to the commercial break. The number one motivator to keep your attention? Fear. Our feeds, radios, and TVs don't encourage understanding. It encourages us versus them. Don't try and understand them. Just fear them. Fear them so you can stick around long enough to the commercial break. Apologies for the hot take. I spent over a decade in legacy broadcasting making the sausage. If you only knew a single crumb of what I know from years on the inside, I digress. So, if we understand something, at least a little bit, we are less likely to be consumed by fearing it. So, what is quantum computing? Basically, and I do stress basically, while traditional computing is based on bits, quantum computers use what are called qubits. A bit, as we traditionally know it, is a mechanical or material representation of an on or an off position. Magnetic particles on a floppy disk, remember those? Or tape storage, the shiny and shadowy areas of optical storage, the holes in ancient punch cards, all commonly referred to as ones and zeros. String 8 of these ones and zeros together and you form a byte. String these bytes together to create a code in your programming language of choice. The processor takes in the stream of code and deciphers what to do with it, like opening an email or subscribing to the Houston Museum of Natural Science on whatever platform you find us. When you plug your smartphone into your car, it uses trillions of these bits and bytes when you ask it to navigate to our museum. And it works really well. You should go ahead and try it. So, whereas a bit can only represent one or the other, a qubit, short for quantum bit, is really trippy. A qubit exists in what's called a superposition. It can represent both a 1 and a 0 at the same time. It is both on and off. Not only that, but its position can be affected by whether or not it's actually being measured. Kind of like Schrodinger's cat. In this thought experiment, the cat in the box is both alive and dead. But it is only one or the other when you actually open the box to observe. A grim mental exercise, really. If someone pointed to a box with a cat inside, you have no idea how long it's been in there. 10 seconds? 10 years? From your perspective, that cat is both alive and dead because you have not observed its actual condition. Such is the state of the subatomic particles that make up a qubit. On the quantum level, it exists in both states until it is measured. That is where things get very, very interesting. Since a qubit is both positions at once, the correct answer to the coded question is in there at the quantum level. To put it another way, the answer to a lot of humanity's unsolvable equations are contained within the output of this quantum code. But how is it deciphered to get a definite binary yes or no answer we can actually understand and use? That is the profoundly tricky part. Now is a good time to perhaps calm some nerves. Despite major breakthroughs like Microsoft's experimental Majorana 1 processor, we are years away, if at all, from a practical, scalable, useful quantum computer that can be put to use in daily life or solve meaningful humanitarian conundrums. In a grossly oversimplified nutshell, the goal of useful quantum computing is to be able to reduce the nearly infinite answers contained within the quantum computer into a quote-unquote probabilistic output of a classical binary computer. This requires truly mind-boggling algorithms to spit out as many probabilistic outputs as possible, and, more importantly, stable, trustworthy quantum particles to facilitate such repeatable outputs. And by the way, these quantum particles typically require being kept at the near absolute zero temperature of outer space and are extremely sensitive to outside interference, which can make them all but useless. Imagine you're in a hot air balloon way high up in the atmosphere. Then you look down and that speck on the ground is a 5-gallon bucket. Now you dump 10,000 golf balls towards that bucket again and again. After each dump, you note which specific golf balls went into the bucket. You pick them all up again and dump them again. You're trying to determine which exact golf balls wind up in the bucket most often. Those are your reliable, stable qubits, and you need a lot of them to be useful. In quantum computing circles, this is known as the path to a million. In other words, we need 1 million reliable qubits in a processor in order to produce usable outcomes. It is unbelievably difficult to harness and decipher observations at the quantum level of nature. So while companies like Microsoft have made fascinating, even tantalizing strides in narrowing down which materials to use to produce reliable qubits, in their case, indium arsenide and aluminum built atom by atom to coerce quantum particles dubbed majoranas into existence, the field of quantum computing is still very much the wild, wild west of computational physics. So, as a quick recap, qubits exist in a superposition as both a 1 and a 0. They currently require vast amounts of energy to produce and are extremely unstable. We need 1 million of them to be useful, and thus far have debatably only managed a few dozen at a time. And even if we are somehow able to create enough viable quantum particles for stable qubits, we still need to develop the quantum algorithms to make use of them in any meaningful way. It would be an understatement to say that the scope of this podcast episode even begins to scratch the surface of explaining the virtually infinite complexity of quantum computing. So I will absolutely include a link or links in this episode description to much more detailed articles that you can sink your teeth into. The intention of this episode of the HMNS Beyond the Bones podcast is not to give you a complete knowledge of this subject, that's impossible, but a general overview that encourages your own journey down the rabbit hole of understanding. Because if we at least pursue a mindset of understanding, fear has less place to hide. Thank you for listening to the HMNS Beyond Bones podcast. If you can rate this podcast or leave a comment, please do. You can also email us at podcasts@hmns.org. I've been your mental curator, Johnny Hemberger, reminding you to stay safe, stay curious, and as always, come out and visit us at the Houston Museum of Natural Science.